Yes, you're welcome to lesson 8. Thank you for viewing our videos. And in lesson 8, I want us to look at cooling curves. And then we understand what are cooling curves and how helpful are they in colligative properties. How do they help us, especially to determine molecular mass of a non-volatile solute in this part of depression of freezing point. So we are saying, what are cooling curves? Cooling curves are graphs obtained. Cooling curves are graphs obtained by plotting temperature changes, by plotting temperature against time during the cooling process of a solvent or a solution. So you could have your pure solvent like water, place it in a container, insert a thermometer in there, and then place the contents of the container with the water and the thermometer, place it in a freezing mixture, and then you start recording the temperature of the water as it lowers down till this substance or this water completely freezes. And then you record that at given time intervals. For example, every after 2 minutes, you record 3, 4, 5. The results of temperature that you are recording versus the time taken can be used to plot a graph, and that graph will result into what we call a cooling curve. Okay, so that means you will go ahead and plot a graph of temperature in degrees Celsius against time, which can be in seconds or minutes. Minutes are more realistic, okay, in minutes, like that. And then you can plot a graph. Now, a typical graph of a solvent and solution would look like this. You could have a graph drawn of this nature. Okay, and then another one. So what do we see? You could be required to name them. I want to call, I can name these ones here very well. The first one should be the freezing point of what? You need to ask yourself, if you see such a diagram, what is above the other one? Is it the solvent, cooling curve of the solvent, or cooling curve of the solution? Using your theory, you should be able to know that the freezing temperature of a solvent is always lower than the freezing point of a solution is always lower than the freezing point of the solution. So the cooling curve that gives the lowest freezing temperature should be the one of the solution. Now the also will be, where is the freezing temperature? In a typical cooling curve, this is what will happen, is that when you're cooling something, when you're cooling any solvent or a solution, the temperatures of the solvent or solution will start to decrease. And as they decrease, it will reach a point when they remain constant. Now the temperature when the solvent starts to freeze, or the solution starts to freeze, is what we call the freezing point. And that freezing point is normally constant. That's why when we are defining freezing point, we say the constant temperature at which the solid is in equilibrium with the liquid. So that means you got your graph and you recognize where the temperature is remaining constant. And on this graph, you can see that we have a section that is constant for both of these curves. So this section here, we can try to trace the temperature on this axis here. So this one could be a temperature for the solvent. And this one is the temperature for the solution. Why I'm choosing temperature up? Because the freezing point of the solvent is higher than the freezing point of the solution. Or what we call the effect of adding a non-volatile solute to a solvent. That this non-volatile solute will lower the freezing point of the solvent. So actually the freezing point of the solution is lower than the freezing point of the solvent. So that's one thing that will guide you to locating which curve is which. So this curve now, I can now say that this is a cooling curve of the pure solvent. And that means the other one is a cooling curve of the solution. Cooling curve of the solution. Now, one thing is remaining for us to name. This part here, this trough here. This trough indicates what we call a supercooling. Supercooling. And the question is, what do we mean by supercooling? Supercooling. Now, supercooling is supercooling of a substance is when a substance is cooled below its freezing point without it freezing due to what we call loss of latent heat of fusion. I can put that one here, that supercooling is when a substance is cooled below its freezing point, without freezing due to loss of latent heat of fusion. So this loss of latent heat of fusion, it is possible that we can cool some substances below their freezing point without them actually freezing. Okay? So that is what we call supercooling. Normally, it occurs during the cooling process. So they can ask you to name that trough. Now, after knowing, how could we use this graph to determine a few things that may be required for calculation of molecular mass? The obvious information that we get from this cooling curve is actually the T0 and the T, so that we are able to calculate dt. Remember, dt is supposed to be T0 minus T, the freezing point of the solvent, subtract the freezing point of the solution. So if this is the only important thing we can get this, then how would the questions look like? I have a sample example here to give you a hint on how questions could look like. The question is saying that the cooling curve of a solution containing 1.2 grams of carbon disulfide. The cooling curve, this is an example. The cooling curve of a solution containing 1.2 grams of sulfur in 20 grams of carbon disulfide and that of pure carbon disulfide are shown in the figure below, and that of pure carbon disulfide are shown in the figure below. So figure below we have okay, so these are cooling curves. So we have temperature here, we have time in minutes here, and then time in minutes. And then we have these graphs here. And then we have another one. Like that. And then we have this is A, this is B, and this is X, this is Y. And we have questions that say identify curve X and Y. Simple as that. Identify curve X and Y. This is part A. They're saying identify Roman 1 curves X and Y. So we could answer this. What is curve X and Y? Roman 2, they are telling us to identify points A and B. Points A, we can identify points A and B. So A and then B. Okay? And then they're telling us to calculate the relative molecular mass of sulfur in carbon disulfide, and they have given us the freezing point depression of carbon disulfide was 1.3. So they are telling us now, let's first name these ones, then we go to part B of the question. Because part B of the question is telling us to calculate the molar mass of sulfur in carbon disulfide, molar mass of calculate the molar mass of sulfur in carbon disulfide, given that Kf of carbon disulfide is 6.1 degrees Celsius per mole per kilogram. Carbon disulfide, Kf of that, and they're saying, and freezing point depression, and freezing point depression was 1.43 degrees Celsius. So everyone who has been watching can actually name X, Y, A, and B, those points. Then my task would be to go to this calculation here. This calculation here. Remember the question started way back from 1.2 grams dissolved in 20 grams up there. Okay, so we can calculate this very fast by looking at what we've been doing. That 20 grams of carbon disulfide dissolve 1.2 grams of sulfur. Because they have given us our Kf in per kilogram, we would ask ourselves, what about 1,000 grams of carbon disulfide? Will dissolve how much? Will dissolve 1.2 times 1,000 over 20. And then we compute the value. Okay? We compute the value. You'll have 1.2 times 1,000 divided by 20, and you will have 60 grams. 60 grams here. So now, that's the stem we had up. And then they are giving us 6.1 here, and the depression in freezing point was given here. So we would now relate. We would now say this is caused by that. So 1.43 degrees Celsius is the T caused by 60 grams. By 60 grams of sulfur. What about 6.1 degrees Celsius is the T caused by 1 mole, which is molecular mass, and will equal to, so you have 60 times 6.1 divided by 1.43 degrees Celsius, and this should give us the molecular mass by computation. You would have 60 times 6.1 divided by 1.43, and we have 60 divided by 6.1 divided by 1.43. We have 2255.94, and this is our relative molecular mass. So you can see that we can as well use cooling curves to get information that can be helpful. There are more examples that we can look at. I've intentionally left you to identify X and Y, A and B, because we did that in the beginning part of this video. When we come back to lesson 9, we shall be looking at something different. Thank you for watching.